What we are about to begin to discuss is called the theory of signal representation. What is representation? The term representation arrives and is encountered in so many different contexts, from politics to signal processing. So, what is representation in general? It is about reducing the number of objects that need to be encountered. That is to say, if the objects in question are signals, then what we seek by employing a representation is a means of dealing with only a small number of signals rather than all the signals that are theoretically possible. If the objects are people, then representation is about a small number of people taking decisions, taking actions on the basis or on behalf of a large number of people. So, that is representation is general. Representation can be said to be the process of replacement of the many by a few distinguished members. So, that is a satisfactory definition of what representation means in the most general context. Now, focusing our attention upon system theory, signals and system theory, what is the need for representation here, and how do we go about bringing up or constructing a representation of signals? Let us understand what we gain by using a representation in the context of signals and systems, and what features, what advantages having a representation will yield to us. All right. Suppose you wanted to have a description of any function. This has already been mentioned in certain earlier lectures of this course. If you want to thoroughly describe any function, and let us say in this context that that function is a signal, let us say it is a function of time, then I had said that you can always represent the function as a virtual lookup table. Any function may be described by a virtual lookup table. All right. Now, in general, a function of one variable will have two columns in this virtual table. The left column would carry a list of all possible values that the independent variable can take, and the right column would carry the corresponding values that the function takes against each value of the independent variable. So, you would have a table that looks like this: values of x on this side and values of f of x on this side. This is what I mean by a lookup table. I call it a virtual lookup table because while in the real world around us a table has a finite number of rows, this virtual lookup table can possibly have an infinite, countably or uncountably infinite number of rows, because there might be that many possible different values for x, and for each of those values of x, f of x needs to be specified. So, we have a virtual lookup table. A virtual lookup table is possibly infinite in size, possibly even uncountably infinite in size, but it is a very useful concept to play with. Now, a general function, be it a signal which maps voltages to time, or rather which maps time to voltages, or if it is a system it maps signals to signals, in all these cases a function is a lookup table, a virtual lookup table. Now, if you want to comprehend the information in the table completely, so that you may put it to use to predict what output will result for the function or for the system when the input is specified, if you want to do this, you normally have to simply memorize the entire table. Memorizing the entire table is certainly a very cumbersome thing to do, especially when the table is very large or possibly infinite. So, when that is the situation, you would like not to literally memorize the entire table, but to find means by which you can calculate the output for a particular input by knowing or memorizing not all possible input output pairs, but only a small number of input output pairs. In short, you want to do the following: simplification of the lookup table. Simplification of the virtual lookup table would result if we could detect patterns in the table. Any sort of regular pattern in the table. I use the pattern here in a the word pattern over here in a very general sense. A pattern can be anything that can be used to make a predicting calculation. For example, if I take the sequence of even numbers, if I want to know what are all present, what all numbers are present in the set of even numbers, one way to do so would be to literally memorize all possible even numbers, which as you know is practically impossible because it is an infinite list. On the other hand, I could have a different means of finding out if a number given to me is infinite or not. If I had a complete list, of course, I would have looked the number up in the list, and if I found the number in the list, I would have reported that it is an even number. If I did not find the number in the list, I would have declared that it is not an even number. That is the brute force way of doing it. What we want to do is, and what as you know we do is, if we want to find if a number is infinite or sorry, if a number is even, we just try to divide the number by 2, and if it divides exactly without any remainder or without any fractional component, then we will say that the number is even. So, we are replacing a huge memory storage by an algorithm, in this case the algorithm of division by 2, and this algorithm is able to substitute for an infinitely long table and making and can make it a finite table which merely tells you what to do, that is divide by 2 and see if the result is an integer. If the result turns out to be an integer, then the original number was even. So, this is the sort of simplification that one is looking for, a simplification where some pattern can be detected using which an algorithm can be designed or can be found, which will give us the answers to the questions we have without having to go back to the brute force storage of all the function values. This is what we want. Okay. Now, what kind of patterns could be there in a general function? For example, let's talk of simplifying patterns in functions. Examples. First example, v of t, or if you like f of t, equals k, let us say. So, this is a function. We want to see if there is a pattern in this function. There is very clearly a very dominating pattern here, which simply says that all rows in this virtual lookup table are identical. So, you just have to know any one row and you know all the remaining rows. This is what you would call a constant function. This is what you would call a constant function. Now, suppose we try something a little more complicated. Let us take an even function, f of x equals f of minus x. This is what we call an even valued function. Now, does this help us in some way? What is the amount of freedom that this function has to express itself? In the first example, that is f of x equal to k, it had absolutely no freedom at all. If you knew f of x for one particular value of x, then you knew f of x for all values of x. There was no room for variation, there was no room for manipulation or change. Whereas now, with the second example, f of x equals f of minus x, we have a slightly looser definition of a pattern. So, lots of signals can satisfy this pattern. All we are saying is, about x equal to 0, the function should have the same value at a point if reflected across the 0 line, the function has the same value at the other point as well. In short, absolute value of x is an example of a function which has a certain amount of symmetry, a certain pattern in it. So, if you want to memorize such a function, you can at least take the shortcut of memorizing one half of it and then declaring this feature of even symmetry. If you say it is even symmetric and if you specify the function from 0 to infinity, that completely helps you to construct the rest of the function on the other side. All right. So, let us look at more patterns. In all cases, as with the third pattern as well, suppose we have a periodic function here, f of x equals f of x minus x 0. Suppose this is what we call a periodic function or periodic symmetry. The whole idea is there a means by which you can have knowledge of only how the function is defined over a part of the domain, and using this knowledge can you construct the entire function. Wherever and whenever you can do this, you essentially have some symmetry or pattern in the function, and that is the kind of pattern that attracts our attention at the present time. If you take a periodic symmetric function, you only need to know the value of the function over one period. Now, if you want to define the function over all time or over all x in this case, then all you have to do is to construct a periodic extension of the function, of the part of the function that you are aware of. That will give us the entire function. So, each of these things is an example of a symmetry. This is a very, very tight kind of symmetry pattern, f of x equal to k or f of t equal to k. F of t equal to k is a very, very strong symmetry. This is a very, very strong symmetry. This is a relatively loose symmetry, because there are lots and lots of functions which still can exist even if f of x equals f of minus x, whereas f of t equal to k, there aren't that many different signals that can have k that can distinguish f of t from each other if they all follow this pattern. This third example is somewhere in between first and second. It does allow certain amount of freedom of expression for the signal. At the same time, it allows the user or the person who wants to follow the signal completely to just follow it for one period and then construct it automatically for all time. So, these are patterns, simplifying patterns that a signal, that any function can have, and whenever you have a pattern, then that helps you to condense the amount of information to be processed. Now, what is true for functions that are signals is also true for functions that are systems. So, suppose you have a system. How do you normally characterize a system? How do you exhaustively characterize a system? If you want to exhaustively characterize a system, you would again have a lookup table, a virtual lookup table, where you would have the input signals, say S on the left column, and here you would say what is the output of the system, which is say P of S. This is the output signal. Now, this being a sufficiently typical example, let us just see what kind of patterns of behavior, desirable patterns of behavior a processor can produce. One desirable pattern of behavior is to say that P of S is a constant irrespective of the value of S over different instants of time. So, you could say P of S okay, that has a very, very nice simplifying pattern. There could be other simplifying patterns that a system can have. Linearity itself is an example of a simplifying pattern of behavior for a system. Alright. Now, how is it a simplifying pattern? Because if I didn't know that a system is linear, or if a system is not linear, then I would have to exhaustively list all possible input signals in the left column of the virtual lookup table for the system, and on the right side for each input I would have to make a record of what possible output will exist. On the other hand, if I just state the property of linearity, that helps us considerably reduce the size of the virtual lookup table that really needs to be carried in order to predict the behavior of the system. So, if you have a linear system, then if you recall, the definition is this. This is a simplifying pattern because suppose you just had one signal, suppose you had x1 now, or s1 as we are calling it. Suppose you had a signal s1. Now, in the lookup table, s1 appears in a certain place, and against it is given the corresponding output of the system for s1 being applied, and that output is p of s1, supposing you know this. Now, tomorrow suppose you wanted to apply 2 times s1 to the same system. Would it have been necessary to also record the corresponding response of 2 times of S1, response to 2 times of S1 on the system? It's really not necessary because the system is linear. If you know that S1 yields P of S1, then 2S1 will definitely yield 2P of S1, as simple as that. So, all cases of linear scale changes in S1 will yield only similar linear scale changes in the output, and thus we could replace a whole collection of different signals which are all scaled versions of S1 by simply S1 and a statement that the system is linear. Alright. This makes a linear system already a kind of already possessed of a certain great simplifying features. Other examples of a simplifying behavioral pattern in a system come out of time invariance. What is time invariance? We had said that suppose you know that xt yields yt, then what would you get if you applied x t minus t naught? You would simply get y t minus t naught, and this would be true for all t naught. T naught. So, the entire set of rows in the virtual lookup table containing signals x t minus t naught, minus infinity, less than t naught, less than infinity, will correspondingly map, because of time invariance, to the change that has occurred over here would be y t minus t naught minus infinity less than this is indeed a great simplification, and it is these simplifying behavioral patterns that lie at the bottom of our seeking after a signal representation. right. Now, what makes the business of simplifying behavioral patterns, what makes them interesting? One thing I said, of course, is that instead of handling the entire lookup table, virtual lookup table of the system, we only have to make a condensed table containing a few representative signals and their corresponding outputs. You do not have to have all the shifted versions of x t. If you have written in the table somewhere that x t leads to y t, then you do not have to worry about x of t minus t naught for every different value of t naught. You do not have to worry about this. Similarly, with linearity, if you knew that x t yields y t, then you would know that k times x t will yield only k times y t. So, you do not have to say over and over again 2 x t will give you 2 y t, 21 x t will give you 21 y t, and so on. You do not have to do it. That is the beauty of having a symmetric behavior in the pattern of the system. Okay. Now, let us see, suppose you have a certain family of processors, a certain family of systems, all of which are possessed of the same kind of symmetric behavior. What I mean to say is, you do not have one time invariant system, but you consider the family of all time invariant systems. Or let us take a different case as a useful example. Instead of dealing with time invariance as a simplifying pattern of behavior, let us look at what I will call flip invariance. I will say that a system is flip invariant if given x t yields y t in the system, in the output of the system, then x of minus t should simply yield y of minus t as well. Fine. Now, suppose you have this property of a system given to you, then you see you do not really have to specify each signal for its entire length. If you say this is the value of x t for 1/2 of time, or rather if you collect the input output pairs for one set of x t, then for all the time reversed signals corresponding to the members in the given set, you already know what value y t will take when x t is changed to x of minus t, y t will change to y of minus t, right. So, this is flip invariance, and you can see that here again the table gets simplified. Okay. Now, what is our objective in using a representation, in seeking a representation? What I am going to say now is probably the most important part of this whole course. So, let us look at it very, very carefully. I will discuss this in a slightly unconventional manner, not the way the textbooks go about it. I am going to discuss this by talking about the system as a map on the signal space. So, the system as a map on the signal space. Let us make a large Venn diagram of what we are looking at. Let us make a Venn diagram. Let us say this is my signal space, I will call it capital S. Now, we know that given any signal, input signal, say at this point, since this is the entire signal space, this given signal when applied to a particular system will yield an output signal which also lies in the entire signal space, because all signals lie in the entire signal space. So, let us say this is the output, then you would go about mapping this input signal to this output signal. Let me call this x t Let me call this yt. Fine. Now suppose you had a different signal x dash t, and this was the corresponding output. Let us say this is y dash t. So then you would say x dash t goes to y dash t, and you would just draw a line which connects this and this. Fine. So for every input signal there is an output signal also in the same signal space. This would be the exhaustive or brute force method of describing the behavior of the processor, behavior of the system. A simpler way would be to recognize that this system has certain behavioral patterns. Thus, what a behavioral pattern gives us is a certain kind of behavior in the mapping of the function. So, for example, suppose we say that there is a subset of the signal space with the property that if you take a signal from within this signal space, then the processor or the system that we are concerned with for the time being will always take this signal to another signal within the same subset. This kind of a subset with this property, that every input signal which lies inside this subset will yield an output signal which also lies in the subset, is what we will call a preserved class. It can be argued that every favorable or desirable behavior pattern that we are trying to seek for the behavior of a system will imply the existence of one or other kind of preserved class. Let us take examples of systems where some kind of a behavioral pattern exists and see what the preserved classes come out to be. We begin this by just taking a simple amplifier. What does an amplifier do? It takes xt to some a times xt. So this is what an amplifier does. So what I do is, in fact, not just this particular amplifier, but if I take any amplifier at all which does just this thing, then I am sure of this much. I am sure that whatever input signal is applied, the form of the signal is preserved by the system, and only its gain or its peak to peak value will be changed. So what I do, I now want to find a preserved class. What kind of a preserved class? Let me take this as a preserved class. Let us see if this is a preserved class. Let us take the set beta xt for minus infinity less than beta less than infinity, okay, where xt is some particular signal, okay, xt is some specific signal. You will recognize that this preserved class, or rather this collection, is indeed a preserved class under the operation of an amplifier, a system that is an amplifier. Any amplifier system, for any amplifier system, this will constitute a preserved class. For different signals x1t, x2t, x3t, you would have different preserved classes, beta xt, beta x1t, beta x2t for all values of beta. So how many signals are there in the preserved class of this sort? An infinite number of signals, because beta can take an infinite number of different values. But yet, if I apply xt to the signal and I get a xt, After all, A is also a number. So, for since beta xt, since this class contains all beta xt for every value of beta, it will also contain A xt. So, if this for example is xt, then this might be A xt. And what if I took A xt itself as the input? Then I would get A squared xt, where A squared is the new value of beta that is being invoked. So, once again it would lie within this set, maybe it would go somewhere here, and this could be A squared xt. So, all scaled versions of xt would constitute a preserved class under amplification. Would together constitute or be a preserved class. Under amplification. So, how many preserved classes do we have for the family of amplifiers? We have an infinite number of preserved classes, one for each different xt that you can think of, which differs by more than a scale factor, by something more than a scale factor from the other xt. Let us take examples. Suppose xt equals cos omega t or cos omega naught t. Now, this is the xt that I have. The preserved class that contains this xt would be beta cos omega naught t, going by the same notation, right. But now suppose I took xt equals sin omega naught t. It is not found anywhere in this class. It is an entirely different signal, and hence it will give rise to its own class, beta sin omega naught t. Minus infinity less than beta less than infinity. All right. Suppose instead I took xt equals cos omega naught t plus theta. This again is not present in either of the above classes. It is an altogether different signal. So, it has its own class consisting of all scaled versions of itself. Suppose you took xt equals mod t. This is another new signal, altogether new because it is not found in any of the previous preserved classes. So, it would give rise to its own preserved class consisting of beta mod t. So, each such signal not found in any other preserved class would give rise to its own preserved class. And the nice thing about these preserved classes is the following. Suppose I took an arbitrary signal and expressed it as a sum of members of preserved classes, then what the system would do to the sum could be simulated by taking collectively into account what the system does to the members of the preserved classes. More clarification on this in a little while, but let me now for the time being proceed with more examples. This notion is so attractive and so beautiful that it lies at the heart of the whole theory of signal representation and transforms. Let us take not amplifiers, but delay networks or delay systems characterized by xt yields x t minus t naught. Suppose every xt is shifted by a factor t naught, and that is what the delay system does. I am really not saying that it is a positive delay, it could be a negative delay, it could be an advance. Now, if we take any delay system, what if any are its preserved classes? Straightforward question, straightforward answer. Take xt, take this as an example, take the set of all x t minus tau for minus infinity less than tau less than infinity. This is a preserved class. Why is it a preserved class? Take any x, take any xt in this class. What is the result of applying the signal to the system? The output will be x t minus t naught. If you apply x t minus tau as the input, it will be x t minus tau minus t naught, which is also already present somewhere else in this class. In short, the set of all time translates of xt constitutes a preserved class for a delay system. The set of all time translates of a given xt constitutes a preserved class for a delay system. All right. So, how many signals are there in a preserved class? An infinite number, because you can have an infinite number of different possible delays. How many preserved classes are there? Again, there is an infinite number of preserved classes for a delay system, because you can have different signals xt, each of which is not found in any other class, and for each such signal there is its own preserved class consisting of all time translates of this. Now, contrast this with our previous example where we were dealing with amplifiers. There what we had was the set of all scales of each xt. For amplifiers, the set of all scaled versions of a given xt constitutes a preserved class. Even more complex examples can be given. For example, suppose we consider the set of all flip invariant systems. What is a flip invariant system? Something we haven't defined as yet. A flip invariant system is defined as follows. If the flip invariant system takes xt to yt,
then the same system should take x of minus t to y of minus t.
We expect a system to be a flip invariant system if it follows this particular definition. All right. This is a flip invariant system. Does this also have a preserved class? Yes, it does. And the way to find that out is to look at the family of all even valued signals. Consider the family of all even valued signals, that is signals
that satisfy x t equals x of minus t.
Now, this set of even valued signals can be shown to be a preserved class for the set of flip invariant systems. How do we show this? Take an even valued signal and apply it to a flip invariant system. It does not matter that we are not focusing on a particular flip invariant system. We are only concerned with any system which satisfies this particular property, the property of flip invariance. Any such system will have the set of all even signals as a preserved class. Now, take any xt, xt should give you some yt. We do not know whether if xt is even, yt will be even or not as yet, but let us go ahead and see what happens.
Suppose xt gives you
yt, right,
and suppose xt is even, then xt equals x of minus t. Because xt equals x of minus t,
even valued signal,
then x of minus t is just another name for the same input xt, and so it should also give you yt.
On the other hand, we have the definition of flip invariance which says that if x of minus t is applied, then the output will be y of minus t. All right. Now, given these two things, it is inescapable that
yt is the same as y of minus t,
which means that yt
is also even valued.
This means that a flip invariant system
takes even valued
inputs
to even valued
outputs, which is very nice, because that means if you take
inside the entire signal space S the set of all even valued signals, which I will call E,
then this family of signals is closed under processing by flip invariant systems. So, as you can see, different kinds of behavioral patterns that might exist in the processor
or in the system will yield certain kinds of preserved classes in the signal space. Of course, the which is the preserved class is what the preserved class is dependent upon what kind of a system we are concerned with. If the system changes, its preserved classes will obviously also change. So, different systems will have different preserved classes, but it often is also the case that a whole family of systems which have a certain common behavioral pattern will all have the same set of preserved classes. For example, the set E, the subset E of the signal space shown in this diagram over here is a preserved class not for one particular flip invariant system, but to all flip invariant systems. Alright. So, that is a nice thing to have. Now, where does this lead us? Where does this pattern of the existence, this behavior of having preserved classes, where does this really help us? What does it give us? In order to understand this question, we will have to go back to what I had said about understanding or modeling the behavior of a system. As I said, one way of describing the entire system's behavior is to maintain a complete lookup table, a thorough lookup table which covers all possible inputs and all possible outputs. But since this is too cumbersome to handle, too cumbersome to process, too cumbersome to store, we are always in the search for shortcuts, and the existence of preserved classes is one possible means of finding such shortcuts. Now, the shortcut that I am about to propose is generic to all kinds of transforms, and all transforms work on this belief that for a certain class of systems they will exploit the existence of preserved classes in order to make a representation. This means two things. The business of signal representation is intimately tied up with the business of processing of those signals. If you want me to identify what kind of preserved classes I should take an interest in, I should obviously start by asking what are the kinds of systems that you will be applying these signals to. Only when the answer to that question is known will I be able to identify and isolate the appropriate preserved classes. So, now suppose you have a set of preserved classes, and suppose further that the system, let us say in the present context, let us just take a simple assumption, let us assume that the system is linear. Suppose a system is linear. That means it satisfies the theorem of superposition. If it satisfies the theorem of superposition, I could either apply a particular signal as the input and observe its output, or I could decompose the signal into a set of components, apply each component separately one at a time, and note the responses and ultimately add all the responses. I would then get a sum of responses whose value is identical to the sum of the components, namely to the original input signal. Fine. This is possible whenever a system is linear. You decompose the signal into components, you have xt, break it up into x1t, x2t, so on, x2t and so on, which are what I call components of xt. I have still not made any, I have not divulged anything about what kind of components, but we will soon be able to put 2 and 2 together about the earlier part of this lecture and the present part, and soon understand what we are looking for. So, then when I have this, I apply each component separately to the system. Let us say that x1t when applied to the system yields y1t, x2t yields y2t, and x n t yields yn t. You have all these different outputs. Because the system is linear, we know that given the fact that xit yields yit, we know that xt, which is equal to the summation of the xit, will give rise to summation of the yit equals to yt. Fine. Furthermore, since the system is again linear, I can take different scaled versions of xit, and I would get the correspondingly scaled versions of the yit, and I could again add them up. Say alpha I xit would yield summation alpha I yit, correct? Okay. Now, we have said all this, but we haven't made any mention or made any comment upon what these components should be. Now, we see that if a system is linear, and if by virtue of its linearity, its homogeneity and its additivity, we can apply a set of components in parallel to an infinite number of copies, a large number of copies of the system, and process each component output separately, then we could recompose the component outputs to obtain the overall output to the overall input. So, what kind of component input signals should we choose? How should we decompose the input signal? How should we decompose the input? This is where those preserved classes come in. Let me draw a big diagram over here, a big Venn diagram. Alright, this is my signal space. Now, in this signal space, I have different preserved classes. This could be one preserved class, this could be another preserved class, this could be a third preserved class, and so on until say this is another preserved class. Fine. Now, one way, as I said, to understand the behavior of the system is to take any particular xt over here and find that it gets mapped to yt over here. But if you try to do that, each xt would be a surprise, because you would know which yt it would go to. What I do instead is this: I first decompose xt, taking one component from each preserved class that is available. So, this x1t will come from here, x2t will come from here, x3t will come from here, xnt, let us say, comes from here. So, there is no need for n to be finite, I am just using it for demonstration sake. Now, this is x1, this is x2, this is x3, and this is xn, let us say. xn. Now, what I am going to observe is this: since these are all preserved classes of the system to which xt has been applied, we can be sure that x1 will be taken to some other y1 lying in its own class. x2 will be taken to some other y2 lying in its own class. x3 will be taken to some y3 also lying in its own class, and so on for xn. It will go to yn, which lies in the same class. Fine. So, that is true for each of the components. Now that you have all the components of the output, they would automatically yield a certain output upon combination. So, the y1 would go to this, y2 would go to this, y3 would go to this, y4 would go to this. They would all add up and they would give you y1, they would give you yt. So, we seem to actually be going through a longer route. We take xt, we decompose it into components, process each component separately, and combine all the output components to get the final output signal. So, what is the advantage in this? The advantage in this is this: you really don't any longer need to memorize the entire virtual lookup table of the system. You only need to memorize the lookup tables of the individual preserved classes. So, the entire lookup table of the system may be replaced by a short collection of separate lookup tables fine. With this, we should be able to handle a large number of signals in the original signal space. Suppose instead I had something over here, this would decompose into something here, something here, something here, and something here. And if it did that, it would give me the corresponding outputs, which would also of course be different from yt or from y1t to ynt, and their composition would yield the corresponding output y. So, you would get this going to this, going to somewhere here, this coming from here, this coming over from here, and this coming over from here, so on, contributing to the reconstruction of the output that would have occurred if you had directly applied the original input without decomposition to the system.